Solubility in pharmaceutical products and dosage form development. The implication of solubility in dosage form is quite essential for us to understand. First of all, the solubility of the drug is a very important physicochemical properties. So the determination of this solubility, of the drug solubility for us as pharmacists, and how to change it, how to alter it, how to make it better, is something very crucial and essential component of our development of our pharmaceutical products. So we go through certain programs and then we try to manipulate solubility in ways that it will increase the benefit of the end product and subsequently the end consumer, which is the patient. We have to put in mind that the bioavailability of an orally administered drugs depends on its solubility in the gastrointestinal tract and the permeability across cell membrane. In this way, there has been some sort of a classification called biopharmaceutical classification systems, BCS, where drug molecules are required to present in a dissolved form in their molecular form, as you recall from our bachelor studies, in a dissolved form, so they should be transported across the biological membrane. So this means that a low aqueous solubility can be related to delay or limit the drug absorption. So it is essential for us to have a good knowledge of the solubility of the drug, and also we should know when it's directly administered to the bloodstream that we can have the desired form. We have also to remember that injectable formulations usually require the drug to be a solution in administration, especially the IV. In addition, drug solution in general is preferred to conduct some pharmacological studies, also toxicological studies during the drug developmental stage. So, in order to understand how these pharmacological and toxicological and pharmacokinetic studies are investigated, we should understand that a poor aqueous solubility will limit the drug's biological application and also put some challenges on the pharmaceutical development. How could you detect the toxicity if the toxicity kit requires the drug to be in its soluble form? Do you understand this? So, in general, there is an investigation, different approaches to enhance solubility as a fundamental and elemental pharmaceutical research step for decades. There are so many labs in different universities and research centers known for their expertise in this field. Also, the need for those approaches are very important when there is some new sciences rising up. For example, there is a rising in the introduction of combinatorial chemistry and high-throughput screening techniques to drug discovery arena. So these techniques will result in rapid development of libraries of pharmaceutically active compounds. And then there is a greater number of highly active compounds that should be investigated in all the way. And those new entities of drugs happens to be extremely lipophilic and poorly soluble compounds. So this will add more challenges for the formulation development process. And you should be aware that more than 1/3 of the compounds registered by Pfizer has a solubility that is less than 5 microgram per ml, poor solubility. Now, a solubility enhancement is one of the primary areas of focus during the drug development phase. There are several situations that sometimes we had to do the quite opposite thing, exactly the opposite, where sometimes a solubility reduction is required. For example, sustained release products or taste masking products, enhancement of chemical stability are dictating us to put some effort to lower solubility. In all situations, in all cases, whether we want to enhance or lower solubility, knowledge of solubility is useful and essential. So, in this way, it is important to determine solubility when developing analytical techniques for drugs. As you're all aware, doctors, that reverse phase liquid chromatography is a very widely used technique for pharmaceutical separation analysis. And as you know, the principle where it's based on the differential affinity of the solute toward the mobile phase and the stationary phase. And a direct outcome of its solubility phases is the result. The analysis of concentration using ultraviolet spectroscopy also performed based on drug solution. So, based on these discussions, it should be clear that solubility is a very important factor that should be studied in pharmaceutical research. And therefore, the determination of solubility is one of the most commonly conducted experiments in the elementary studies. Sometimes there are challenges, but a number of experimental variables may affect the solubility, and then you should be aware of them before conducting those experiments. And we need to understand how to exclude the high degrees of scatter in data. And based on this, a knowledge of different techniques that has the applicability of tools for the estimation of solubility based on the theoretical calculation is included. And most of these calculation approaches are useful with respect to providing reasonable estimation and saving time. But either situations or softwares or sophisticated mathematical models, even if they save time and they give reasonable estimation that you can rely on, still experimental determination is important and cannot be replaced. In general, when we start to estimate it, we should understand that solubility is actually the net result of interactions between different molecules. So you need to remember the strength of molecular interaction with intra and intra that will affect the solubility. For example, you need to remind yourself that ionic interactions which occur between two oppositely charged ions is there, and this could be observed in pharmaceutical salts and ion pairs. Also, when you have two molecules with permanent dipole moment that can interact when replaced in sufficiently close proximity, for example, ketone interaction, this is observed in what we call van der Waals interactions. And the molecules usually try to arrange themselves in order to have a lower energy levels. Also, there is London force, which are commonly known as dispersion interactions that occur when there is any adjacent pairs of atoms or molecules that are present in sufficiently close proximity, where these interactions account for the attractive forces between the nonpolar organic molecules and the non-ionic molecules. Also, you need to remind yourself with hydrogen bondings that occur when there is a hydrogen bond donating groups and strongly electronegative atoms such as halogens, oxygen, or nitrogen. Hydrogen atoms becomes more associated with electronegative atoms by virtue or electrostatic, and as a result, they form hydrogen bridges. These interactions are prevalent in aqueous and alcoholic systems. Now that you have a summary of reminding ourselves, of the types of interaction that is expected, we need to remind ourselves of the approaches of solubilizing drug candidates. In general, equilibrium solubility is dependent on the properties and nature of interactions in solid state as well as in solution state. So we need to make certain modifications. Sometimes it's related on the drug, sometimes it's related on the environment. For example, the use of prodrugs, metastable crystal forms, amorphous states of drugs, salt formation, co-crystal formations, all of these are techniques that have been verified and used. However, in solution states, when you have weak acid or weak base drugs, ionizable drugs, solubility can be changed and influenced by altering solution pH or adding some additives like complexing agents, surfactants, or co-solvents. Now, for orally administered drugs, we need to focus on the solution rate, which is not only dependent on the physicochemical properties of the drug itself, but it's related to the environment, which is the physiological conditions of the GI tract, for example, the transit time, the bile salts presence, lipid contents, and intestinal pH. Now, in order to enhance solubility, we need to go for certain techniques as we mentioned earlier. We will start by the effect of pH on solubility, where important numerals of drug candidates are either weak acids or bases and their salts. Therefore, solubility can be easily modified by changing the pH of the aqueous medium and the electrolytes in solution. The ionization equilibria and the intrinsic solubility of the unionized form species determine the nature of dependency on the drug solubility on the pH. This is a figure to remind you how pH of a weak acid can be enhanced by altering the pH. The other technique, rather than using pH alteration, is the use of complexation, which is a reversible non-covalent interaction between the molecules of a drug and a ligand. So it is possible for a drug to interact with the ligand to form more than one complex with different stoichiometry. Complexation is best studied using a phase solubility diagram, where you study the solubility versus the ligand concentration, as you see here. Also, we can use to enhance solubility co-solvents. So co-solvents are co-solvent water mixtures with similar polarity to the drug can lead to a greatest enhancement in the drug solubility. So the drug solubility versus co-solvent fracture usually follows a log linear relationship. That is, we estimate a high solubility once we change to a co-solvent. However, the use of co-solvents, although it enhances the solubility in good ways, but it is limited due to toxicity, especially at high concentration, toxicity of the co-solvents, of course. We also need to remind ourselves that sometimes using two co-solvents with water can also increase the solubility in good ways, and then maybe if you use synergism effect and lower concentration of both those co-solvents could lead to a better solubility with lower toxicity. Another technique that can be used to enhance solubility is solubility using surfactants. As you are aware, the surfactant monomer can reach the critical micelle concentration, which is the lowest point of surface tension reduction according to addition of those surfactants, and then those surfactants start to assemble in the solution, forming something we refer to as micelles. So in the drug solubilization by surfactant, the drug is assumed to be incorporated in the hydrophobic part of the micelle. So this is, as you're aware, this is a micelle in an aqueous medium where the hydrophilic head is directing toward water, while the hydrophobic part is inside. We usually refer to as hydrophobic tail, and the drug is usually expected to be absorbed in the hydrophobic tail. Now, as you're aware that there are certain techniques and rules to use every approach, of course, you cannot use pH alteration for a nonpolar drug, but wherever both two techniques are possible for a certain drug candidate, as you understand how to make a rationale of it, it is a common thing to find that single approach is not usually adequate to improve the drug solubility. Therefore, sometimes a combination of ionization with co-solvency, complexation, or micellar solubilization can show a synergistic improvement of solubility of weak electrolytes. And this is often what actually happens in the labs. So, how to estimate the solubility in experimental way? There are various aspects that need to be understood for solute and solvent of interest, experimental conditions, and determination of the proper analytical techniques employed. All of these, they will actually affect the determination of actual solubility. In whatever technique or conditions are selected, in general, the very first step depends mainly on saturating the solvent with the solute and then measuring the amount of the solute present per unit of the solvent at that saturation state after reaching equilibrium, of course. So a variety of analytical techniques can be used, and this we will be studying during the course, and I think that advanced instrumental analysis have helped, the course have helped you in understanding some of these techniques, of course. So you can use different analytical methods in order to detect the concentration of the dissolved solute. Now, before designing the solubility experiments, we should identify the requirements to determine the thermodynamic equilibrium solubility, or if you want to understand the kinetic dissolution rate. So, if the goal is to prepare a liquid formulation, then equilibrium solubility information is more meaningful for us. However, if we need to understand dissolution rate, this is the case when we need to understand the release of a drug from the formulation and the subsequent absorption that will be affected in the gastrointestinal tract. So usually, as we mentioned earlier, we can go for phase solubility technique as a conventional way to measure the equilibrium solubility. We usually start with adding excess amount of the solute in the solvent in a closed container and then shaking it for a sufficient length of time. Once equilibration is occurring or maintained, or we can ensure it occurred, then the phase separation is the next step to remove the undissolved solute and then analyzing it in a quantitative way. using different technique, for example, UV absorbance, HPLC, UPLC, you name it. It is necessary to maintain the same temperature for equilibrium during this experiment, even though through the phase separation process. Now, this technique usually is very informative, but it consumes time. And if we need to run different solubility for a large number of candidates at the early phases of discovery, then you need to understand that it will consume time and sometimes consume a huge amount of solvents that all will be discarded after having the enough replicates. Finally, we would like to say, to highlight a couple of things. So when we said here that we need to add excess amount and shake them for a sufficient length of time, and then we need to separate them, we would like to draw your attention that there are experimental consideration. Once you establish this experiment should be taken and studied well before starting your experiments. For example, the shakers and containers. Appropriate shakers to be selected in order to ensure proper wetting. So there are a variety of things like end over and shakers, rest action shakers, those that you can select, for example, depending on the volume of the solvent, depending on the viscosity of the solvent you need to use. Also for equilibrium, it's quite difficult to go with time to achieve equilibrium, but it's very essential and important. So sometimes multiple sampling is required to understand the time it takes for equilibrium. Is it 2 hours, 8 hours, etc. For the phase separation, which you may think it's as well a very basic technique, even the filtration, which is very recommended for this step, there are different commercial filters that is available on the market. They have different sizes, poor dimension. The membrane materials sometimes affect our experiment. So you really need to understand all these factors, determine them all before starting your experiment. All the best. Thank you for attending this lecture.